Sedimentary rocks are the most important rocks near the surface of the planet. But this may seem like a bold statement. Yes, I study sedimentary rocks, but igneous and metamorphic rocks make up over 90% of the Earth's crust, and they make up an even greater percentage of the planet as a whole. But the critical word in that declaration is surface. 75% of the Earth's surface consists of sediments and sedimentary rock. So while sedimentary rocks are just a small fraction of planet Earth overall, most sedimentary rocks are located right where we can see or study them. Even better, the Earth's surface is where life and weather and climate interact with geology. And sedimentary rocks form in ways that allow you to interpret past environments and climates of the Earth's surface. It gets even better. If you're interested in fossils, most of the time you're searching in sedimentary rocks. The relatively gentle ways that sedimentary rocks form results in preservation of fossils. That is, they lithify, turn into stone, at low temperatures and pressures in comparison to igneous and metamorphic rocks. Additionally, in many localities, sedimentary rocks also contain resources like coal and gold. Coal is mined from sedimentary rocks that formed in swampy environments that support abundant vegetation that is frequently submerged. And gold? Gold is eroded from gold veins in solid rock, then transported and deposited in river sediments. Other important resources are derived directly from sedimentary rocks, like oil and water. For example, groundwater is pumped from sedimentary rocks. At much greater depths, oil is pumped from sedimentary rocks. Other resources that can be extracted from sedimentary rocks with increasing amounts of effort are lithium, easy, phosphate, takes some processing, and manganese, even more processing. For geology, what is probably the most important thing about sedimentary rocks is that they provide a record of Earth's history through much of geologic time. When you read the rocks for Earth's history, frequently it is a sedimentary rock that is telling the story. The word sedimentary comes from a Latin word meaning to settle. Sedimentary rocks are formed from the deposition or accretion of particles that are generated in two ways. First are particles of the rock derived from broken fragments of pre-existing rocks. This type of sedimentary rock is called clastic. The second group of sedimentary rocks consists of particles that are either chemically precipitated, like a salt, or biologically produced, like shells or skeletal parts. For this lesson, we'll focus on clastic sedimentary rocks, also known as detrital sedimentary rocks. Clastic sedimentary rocks form as the culmination of several processes that together also constitute a sort of rock recycling process. This process starts with weathering, the breakdown of rocks in place. Weathering creates both new minerals and smaller pieces of pre-existing rocks and minerals. Then there's erosion, the process of removing and transporting those small particles to a new destination. Transportation can be provided by water, wind, gravity, or ice. Next, deposition occurs. When the transporting medium loses energy, the accumulation of sediments occurs in lakes, bays, and the ocean. At some point, sediment transitions to sedimentary rock, a process called lithification. This occurs by compaction and cementation of accumulated sediment. With deeper burial and higher pressures, chemicals in sedimentary rocks will alter. For example, organics in the rock can form kerogen, which is made of hydrocarbons and goes on to form petroleum. The sum total of all changes that happen to sediments as they change into rock is called diagenesis, from Greek, dia for change, and genesis meaning origin. In the previous two lessons about rivers and shorelines, we already talked a lot about environments that are dominated by clastic sediments. Rivers erode existing rocks and transport those eroded particles. At the shoreline, transport is by wind, currents, and waves. It is the clastic sediments that have been generated, transported and deposited by rivers and oceans that dominate the near-surface geologic record. There are great examples of spectacular clastic sedimentary rock exposures throughout the U.S. The Badlands of North and South Dakota, eastern Colorado, and Nebraska. These areas resulted from Cenozoic rivers from at least 35 million years ago, flowing from the uplifting mountains to the west and carrying clastic sediments eastward. The checkerboard mesa of Zion National Park is an ancient sand dune. A hallmark of the Appalachian Trail are the quartzite ridges. These are the ancient shore deposits of sand that lithified and later experienced metamorphic levels of heat and pressure. Clastic sedimentary rocks are classified, in part, based on the size of the sediment particles. From small to large, clastic sedimentary particles are clay, silt, sand, and gravel. It turns out that each of these can be useful. All sizes of sedimentary particles have economic value. Clay, as I mentioned in the previous lecture, is a very fine-grained sediment that collects in very slow-moving water. A lake, for example. Clay is used for landscaping because it is easy to work with, and when moist, it binds. Landscaping clay is an important part of America's pastime. A professional baseball infield uses manufactured sediment that is 30 to 40% clay, an ideal mixture determined through trial and error. Any more clay and the surface would be too hard, but any less and the infield wouldn't absorb rain. 8 to 10 tons of clay go into a regulation pitcher's mound alone. And this clay is special stuff. In the old days, material was gathered near Palmyra, New Jersey, from a Delaware River tributary location that was a closely guarded secret. Similarly, these days, 21 professional stadiums use infield clay mixtures from western Pennsylvania that are manufactured near slippery rock. Clay is also useful when baked. Traditionally, clay has been the key material in making bricks, ceramic roofing tiles such as terracotta, and traditional ceramic dishware. And yes, clay can also vary by composition. People often ask whether whatever sedimentary clay they're looking at is the same stuff that is used in cosmetic clay masks or medicinal clay. In general, the answer is no. Frequently, clay used in landscaping and brickworks has been mined from an accumulation of clay that was transported by rivers and deposited. There is another clay product that forms from the weathering of bedrock. That clay is mined right where it formed. The word clay, in this case, applies to a specific group of minerals that have a unique layered structure. Some of these are aluminum silicates, such as kaolinite. I have an example here. Kaolinite was famously mined at a site called Kaolin, meaning high hill. When purified, kaolin is white, absorbent, and chemically inert, which is why it's used in everything from cosmetics and toothpaste to inks and paper. Silt particles are somewhat larger than clay particles, but even silt-sized grains cannot be seen with the naked eye. To tell the difference between clay and silt, you can use your sense of touch. For example, you can rub grains between your fingers. Dry silt will feel a bit rougher. Or you can put them in your mouth. Silt will make a gritty feel in your mouth. Clay will feel smoother. Great stuff. When they're wet, both will look like mud and often be found mixed together. But wet silt will feel more slippery. While the more clay there is in your sample, the more the mud will feel sticky. Silt is especially important in agriculture. Silt can be added to soils to improve crop yield. It will both retain water and increase airflow in soils, especially in clayey soils that can be too stiff for plants. Where silt becomes a problem is when there is too much of it in a river or a canal. The bigger the sediment particle, the faster they sink. In calm waters, sand grains sink in less than a minute. Silt grains sink in less than an hour, while tiny clay particles may take days or even longer before they sink. But wherever water is constantly moving, silt particles that have settled out will be churned up again and again and again. Silt can choke up a canal or river. This will decrease flow rates and cloud up the water. This is why a river is said to be silted up rather than clayed up or sanded up. Too much silt in water will also have a harmful effect on fish or other living things. Sand, by contrast, is the first sediment particle of a size that sinks rapidly in water and is large enough to see. If you're nimble enough, you can pick up a sand grain to study the mineral composition. Most sand mined in the U.S. comes from unconsolidated sedimentary units, whether deposited by rivers, collected at shorelines. Sediments that have been deposited but not yet transformed into rocks are called unconsolidated sedimentary units. Engineers sometimes refer to material made up of loose particles as aggregate or even soil, but geologists say sediment. Countries with a marine shoreline, such as Japan, often mine unconsolidated sand offshore. Sand has a lot of uses. Building materials such as concrete, cinder blocks, and clean fill all have a large amount of sand. Playgrounds, golf courses, volleyball courts, and sandboxes use sand because it is clean, mostly quartz. Sand is abrasive, think sandpaper, so you can use sand to distress a wood finish or condition tools or glass jars and containers. Sand mixed with paint will make a step a little less slick. Sandbags are used to hold back floods because they are impermeable, and in most places, sand is readily available and inexpensive. Sand is also easily put into the bags and easy to dispose of after use. Most of it ends up in gardens. Note, the sandbags used for floods are different from the sandbags used for weight training. Regular sand, as it grinds together, will generate an annoying dust during weight training. Some lithified sand units are mined. Because of its consistent shape and mineralogy, sand from ancient sedimentary rocks is mined in central North America. Industrial uses include sand for hydraulic fracturing, well packing, cementing, and glass making. It is an amazing resource. Gravel, the next larger size particle, together with sand, make up an important but surprising mineral resource. In a number of states, sand and gravel make up the #1 economic mineral. Over 1 billion tons of sand and gravel are mined in the U.S. each year for use in concrete, building materials, and road fill. Worldwide, it's 50 billion tons of sand and gravel, more than 10 times the amount of cement or iron. So clay, silt, sand, and gravel are the sedimentary particles that make up clastic rocks. With burial by overlying sediments and compaction, and with cementation, which is the infilling of natural chemicals between the particles, a loose aggregate of particles becomes a sedimentary rock. Let's take a look at some typical clastic rocks. They're grouped here according to grain size, with the fine-grained rocks on this side and the coarse-grained rocks on this side. The fine-grained rocks, siltstone and shale, are not subdivided. In hand sample, you can't see the individual grains. Shale is made up of clay, siltstone is made up of silt. But they are still important. Altogether, the fine-grained sedimentary rock, broadly called shale, account for over half of all the sedimentary rocks on Earth. But the rocks that have grain sizes that are large enough to see are subdivided on the basis of composition. The sandstones, made of sand, are arenite, arkose, and greywacke. Each have different compositions. They also have different grain shapes. A conglomerate made out of gravel has smooth clasts and rounded clasts. Breccia, where the gravel clasts are more jagged. But grain size does more than offer a basis for classification of clastic sedimentary rocks. Grain size also allows you to begin understanding the origin of the rock, because grain size indicates energy levels of transport mechanisms. For instance, here's a conglomerate. It's made up of pebble-sized particles and some particles the next size up called cobbles. What environments have we seen in past lectures that can transport these larger particles? The answer is, these larger particles need fast-moving water, whether from rivers or large waves in coastal waters. Clastic sedimentary rocks with large particles are considered high-energy deposits, and fast-moving streams and large waves are considered high-energy environments. But what about particles even larger than cobbles? Large class conglomerates show up in beach deposits. An example is Parfrey's Glen State Natural Area in Wisconsin. These deposits, called tempestites, form when boulders have been tossed up onto beaches during major storms or hurricanes. In the case of Parfrey's Glen, these rocks take us back 500 million years to a time in the Cambrian period when this beach would have been an island near the equator. This was a time when almost half the globe was covered by a single ocean called the Iapetus Ocean. The storms would have been incredible. Now let's look at a conglomerate exposed on Antelope Island State Park in the Great Salt Lake of Utah. Antelope Island is a geologic paradise for a lot of reasons, but the Mineral Fork Formation is really spectacular. Good exposures occur along Elephant Head Trail, where boulders over 6 feet in diameter occur regularly. The Mineral Fork is an ancient deposit of a pre-Cambrian glaciation, and these boulders were transported by a glacier. Glaciers can move even bigger rocks than hurricanes, so this would have been an exceedingly high-energy environment. You get the idea. The more energy in the system, the bigger the sediment particle that can be moved. Class characteristics also tell you something about the origin of sedimentary rocks. Here's another hand sample of a coarse-grained sedimentary rock, but it's not a conglomerate. It's called a breccia. The individual particles are angular and have points and corners. Why is that? Prior to deposition, these angular particles were not subject to substantial rolling and impact with other particles. They were probably transported a very short distance. Hence, the angular nature was preserved in those clasts. Frequently, landslide deposits have this kind of angular clast. Conversely, the more a particle is transported, the rounder the edges become. This principle can be observed with sandpaper. The grains either get worn off the paper entirely, or they become worn down and smooth from all the movement of the sandpaper. As a result, the paper itself becomes less effective due to the rounding of grains. Similarly, sandblasters have to keep renewing the sand particles that they use because the individual grains become rounder with use and after time no longer abrade as efficiently. So clast roundness or angularity tell you about the amount of transport. Another difference that is important for the interpretation of sedimentary rocks is composition. Look at these sandstones. They're all made up of sand-sized particles, yet they look very different. It's the composition. The particles are the same size. All the sediments are grains of sand, but the composition is different. When particles are almost all quartz, like this rock, we have what a sedimentologist would call arenite. When quartz occurs with feldspar, we have arkose, which is probably the most common type of sandstone. This stuff has the same ingredients as granite. It looks a lot like granite and is formed when granite breaks down due to weathering. In the last sample of sandstone, quartz and feldspar are mixed with mica and other rock fragments, a big mix of things, giving us a so-called dirty sandstone, also known as greywacke. Why the difference in source material for these three types of sandstone? It has to do with both the source rock and the history of the sand. Over time, the transport and grinding of sediment together will wear down individual grains to a smaller size in a process called comminution. Rock fragments and mica of dirty sandstone will grind away first, and then feldspar. Ultimately, the last thing left is quartz. Quartz is one of those minerals that is very resistant to breaking down, either by weathering or erosion. That's why a lot of beach sand is mostly quartz. Even with waves breaking on it and currents transporting it, quartz will persist. This, of course, makes for a great white sand beach. It also makes for a useful resource. The extent of the removal of all other things besides quartz and sand is known geologically as maturity. Sandstones that contain 99.99% quartz are known as ultra-mature or ultra-pure sandstones, and they occur frequently in the rock record. Ultra-mature sands are often used in the manufacture of glass. It was in Venice in the mid-1400s that the technique of melting ultra-pure sand and soda ash to generate clear glass called cristallo was invented. In the early days of industrialized fine glass making, companies would locate themselves close to geologic formations that contain both ultra-pure sandstones and coal beds as an energy source to melt the glass. This is how famous glass companies grew up in Germany and Ireland and in the US. A third consideration was reducing the shipping distance of the final product. In the early days of the industry, fine glass would break frequently during transport. So places like Corning, New York and Pittsburgh, PA, that were close to all three, a source of ultra-mature sandstone, a coal source, and a market, became the home of glass companies. My grandfather came from Ireland, where he learned glass blowing, to work just west of Pittsburgh at the Phoenix Glass Company in the Beaver Valley. The composition of a clastic sedimentary rock can also tell you where the rock and its individual particles come from. This is known as the sediment's provenance. Provenance of sand played a role in a little-known event during World War II. The Japanese military thought an attack on U.S. soil would be a tremendous blow to U.S. public support for the war in the Pacific. Because the Japanese did not have the military capability to fly bombs to the U.S., they used hot air paper balloons carried by the jet stream to deliver bombs to the U.S. It took balloons several days to weeks to travel across the Pacific. Probably close to 9,000 balloons were launched. Sadly, 5 kids and a pregnant woman on a picnic outing were killed in Oregon when they happened upon one of those bombs. These were the only documented deaths in the 48 continental states of the U.S. during the war. Of course, the U.S. military was aware that this was going on, and they also realized the potential of this kind of news for propaganda purposes. So the U.S. government asked newspapers to keep this quiet. And today, it is still not a well-known part of history. Behind the scenes, officials noticed that the use of sand in the ballast, the weight used to keep the balloons at the correct elevation for the jet stream, they recognized that that sand did not come from North America. A geologist at the USGS determined not only that it was a beach sand of a distinctive composition, but that the presence of fossils in the sand predicted a specific latitude for the provenance of the ballast sand, leading to 2 beaches on Japan's main island of Honshu. The U.S. began a series of bombing runs targeting that area and the Japanese factories that made hydrogen in the balloons. Soon after, the Japanese military discontinued the program. The next thing I want to show you are sedimentary structures. Your ability to really read the rock record takes a big leap with an understanding of sedimentary structures. These are features formed at the time of deposition that provide information about the environment that the sedimentary rock formed in. I have some examples here. By far, the most important sedimentary structure is bedding, also known as strata. So the study of geologic beds, or strata, is called stratigraphy. When first deposited, most bedding layers are horizontal, but there are some common examples where beds are not horizontal. Crossbedding forms when particles are being transported and there is a change in the transport direction, whether a change in the flow of a stream or the change in a wind direction on a beach. Ripples are another sedimentary structure. Ripples form on the sediment surface as wind, river currents, or waves move particles in the direction of flow. If the current is moving in a back and forth motion, like waves up and down the shore, the ripples, like these, will be symmetric. If the current is moving in one direction, like a river does, the ripples will be asymmetric. Other sedimentary structures form as a result of biologic activity. Take a look at these. We can see burrows, tracks, and trails. In general, such activity is called bioturbation. Burrows, tracks, and trails show you how an animal moved, how big the animal was, and sometimes how many animals were present. I was once at an exposure in the Karoo Basin, South Africa, where 3 reptiles from the Permian age had wallowed in a mud pond to keep cool while small fish swam around them. When they stood up, the reptiles would shake off the mud on their undersides, like dogs today shake off water. The site preserves 240 million year-old splatter marks. These are amazing sedimentary structures. Some sedimentary structures form as a result of a unique event. When there is an underwater landslide, the formation of graded beds or turbidites is the result. The watery, muddy sediment moves rapidly down the slope, and the largest particles settle out first. The smallest particles settle out last. But it all happens as part of the same event. Earthquakes can trigger a submarine landslide, and that's why multiple turbidites found together in a sedimentary unit can be an indication of mountain building events. Desiccation cracks form when wet sediment dries out. This can be from the alternation of high tide and low tide, or desiccation cracks can preserve a long-term climatic warming event from the past. Some sedimentary structures show us a brief event that is hard to believe is preserved in the geologic record. We sometimes find evidence of things like raindrops. These are 250 million years old. A single stone dropped by an iceberg floating in a glacial lake. So-called soft pebble conglomerate. A soft pebble conglomerate is the result of a single storm that was strong enough to pick up thin crusts of beach sand, yet not so strong to break them up. You can see these cracks that indicate they broke after they were put there, but still soft. To give you a feel for soft pebble conglomerates, I always tell students about a time one winter when my wife and I were walking along a cove on Martha's Vineyard. A thin layer of ice formed over the water, as happens with the formation of soft pebble conglomerates. During the night, the wind blew the ice up on the shore in slabs, but didn't break them up. As it turned out, the ice was thick enough to lift up. It was like a pane of glass, but thin enough so that it didn't hurt when we broke them on each other. It was a fun and special morning. And a soft pebble conglomerate is the same, except that the hard part is the sand. Under the water, you get a little class of semi-hard sand being pushed up with little pebbles. The environment of sediment deposition and the conditions at the time of deposition dictate the type of sediment that will accumulate. Let's think about that in a bedded or stratified rock. What if there are different sediments in different beds? What may have caused this? Say the first bed is a sand. Next, and you frequently encounter this in the field, is a siltstone or a shale overlying a sand. Think about it. The sand particles are larger and will have been deposited by more active waters, say on a beach. The smaller clay and silt particles of the siltstone or shale were deposited in deeper and calmer water. Deeper water deposits overlying a beach, or shallow water deposits indicating a sea level rise. To see a famous example of shale overlying sandstone, we can look at the Grand Canyon, where the Bright Angel Shale overlies the Tapeats sandstone. The sandstone is harder, so it forms cliffs, whereas the shale is softer and it forms gradual slopes that break up and are also more likely to have vegetation. To sum up, at the point of sedimentary transitions, we are looking at a time when conditions favoring the deposition of one type of sediment cease to exist, and conditions favoring the deposition of a different sediment began to exist. And at the heart of it all, that's always the point. There's been a change. You might notice it when you're seeing the thinnest bedding on a hand sample of rock. Here's an example from the Dolomites, where the transition from silt to sand is caused by tides, or these slightly thicker beds transition from silt to clay caused by the transition from summer to winter and the freezing of the lake. Or it might be a large-scale difference in strata exposed in the canyonlands. But the strata in all cases mean the same thing. Some kind of change has occurred. Sedimentary rocks make up a small minority of the rocks on Earth, but a substantial majority of the rocks at the Earth's surface. And as we'll see again and again, whether you're looking for water or fossils or geologic resources, sedimentary strata are often your best or only place to look.